All right. Hello, friends. Welcome to lesson 10.3 on 3D formulas. Lesson in which we're going to take a lot of the formulas we already know using the coordinate plane and apply them in 3 dimensions. So if you're familiar with those and remember them, this is a pretty simple lesson for the most part. So let's take a look at some definitions and we will get started. Okay. So the first definition is polyhedron, which is a shape formed by four or more polygons. So this would be excluding cylinders or cones, or let's go ahead and add another one up there. That also excludes spheres, or cones or spheres. So a polyhedron is basically not, I wouldn't say prism, but yeah, it's a 3D shape that doesn't involve a curve. So you could have a nice little pyramid like this. You could have a nice little prism. Okay, any of these are your polyhedrons, whereas what are not your polyhedrons are things like a sphere, which we haven't talked a whole lot about yet, or a cone. And so the only reason I think they point that out in this lesson, I'll cross those out, is because the formulas that we're looking at today really only apply to the polyhedrons, those with like polygon bases, polygon sides, versus those with the curves and the spheres. Okay, so that's a polyhedron. Then we get this thing called Euler's formula. And I'll be honest, not going to have a whole lot of application of this, but it is, you will get asked about it on standardized tests. You will get asked about it in this chapter. And so it's a pretty simple thing, though its application is you're not going to use it a whole lot beyond just knowing it. And what it is it's a way that the faces, edges, and vertices of a polyhedron relate to each other. Kind of a way to solve and find one of them if you don't know them, or to, and probably is more useful with more complex polyhedrons with lots and lots of faces and sides. But anyway, there it is. It's a formula that always equals 2. It's the vertices minus the edges plus the faces equal 2. So we'll just do a quick example here using our drawing. Our cube or our square prism or our polyhedron. And so we start with the vertices. So the number of vertices are 1, 2, 3, 4, 5, 6, 7, 8. So we've got 8 vertices minus, okay, so then how many edges? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Or let's see. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we can subtract our 12. And then we're going to add our faces. So 1, 2, 3, 4, 5, 6. So we've got our 6 faces. So 8 minus 12 is -4. -4 plus 6 equals 2. So we can see that we correctly counted and accounted for all the sides, all the faces, edges, and vertices of that cube. And again, it's just kind of a way of checking that you have those accounted for properly, or in a more complex polyhedron, you can solve for. If you know the number of vertices and edges, you can find the number of faces that thing has. Or if you know anything, if you know the edges and the faces, I can find the number of vertices. Which, if they describe something as simple as a cube, you might be able to figure out otherwise. But if they give you some sort of 59-sided shape or something much more complicated, you can use Euler's formula to find one of the missing components. Okay. So we move on then, we have diagonals, okay? So within polyhedrons, you have diagonals, which are defined as going from one corner across to the other corner. So if you could imagine that in 3D, I'm starting in the back left corner and coming all the way to the right front corner. And just like we found hypotenuses with right triangles, so in 2 dimensions, we were dealing with this shape. Now what we're basically doing is having a formula that allows us to solve for 3D hypotenuses. That's how I would think of this. The diagonal is like a 3D hypotenuse. And so if you look at the formula, that diagonal is equal to the length squared plus the width squared plus the height squared, and then you square root that. Okay, so that's just like what we normally do, where we had a squared plus b squared equals c squared. But now you're dealing with 3 dimensions, but otherwise the formula is exactly the same. And so in the questions below, we'll solve one just like that. Okay, so we have diagonals. Then now we take the coordinate plane into 3 dimensions, what's called called space, and that is where, and you want to start to visualize what I've drawn here in 3 dimensions. You have an arrow that's coming towards us. That is this one right here. We're going to call that the x-plane. So x is a certain number of units forwards or towards you. And of course, that's moving up here is moving back into the distance. Okay, then y is then your horizontal distance here. So you've got a forward distance and then a sideways distance, or forward and back, side to side. And then z is that vertical axis right here, up and down. And so now we can place points in 3 dimensions. So for example, if we said, okay, I want to locate 2, -3, 5. Okay, and again, it's got length, width, and height. So it's moving in 3 dimensions versus 2 dimensions, but otherwise it's the same idea. So here, again, you're going to have to reorient yourself on the axes, because we're used to using this right here as the x-axis, but that's no longer the case. 2 is now forward. So x2 would be right up here, 2 forward, and then it would go 3 to the left because it's -3. So 1, 2, 3. And then it would be 5 up. 1, 2, 3, 4, 5. So it's like it came forward 3, moved left. I'm sorry, forward 2, left 3. That looks kind of ugly. Let me fix that. I'm going to change colors. So it comes forward 2, left 3, and then up 5. And so it's that idea that that point would be kind of located somewhere right about here. And again, you got to picture it in 3D space, where it's come forward, gone to the side, and then up. And it's floating out there. 2 out, 3 to the screen's left, my right, or the origin's right, and then 5 up above. So kind of tricky to visualize, but we'll practice and we'll get good at it. We have a 3D coordinate plane known as space. And then we get the 3D application of our distance and our midpoint formula. Again, one of the skills that we worked on in earlier chapters, almost at the very beginning, was how we could take any 2 points in 2D space, and if we connected them, we could calculate this distance. If you remember, that was basically, we used the Pythagorean theorem, where you had a squared plus the b squared, and it gave you c squared. And we could also calculate the midpoint of that, where we basically added x and y, or x and the other x divided by 2, and the y plus the other y and divided by 2. Okay, and so we had these formulas in 2D, but just like with the diagonal I drew up here, we can find any distance between points in 3-dimensional space as well as the middle point. And we do that simply by using the same old formulas, but if you notice here, with the added dimension z. So what you have up there is the old distance formula, where you find the distance between the 2 points. That's a and that's a squared and b squared. You square them, but now we add the distance between the z points, and then we square root all of that, and that will give us the distance. It's pretty similar to what you're doing right here with length, width, and height. Only here you're using a point, so you have to subtract here and here to find those lengths. But otherwise, it's the same formula as the diagonal formula. And then you can see the midpoint is the same as our other midpoint formula, but now you just have the 3rd dimension z. So really nothing new if you're comfortable in remembering those formulas. And again, you're finding the length of these 3-dimensional lines, and also the location of the midpoint on those 3-dimensional lines. And we'll do down here in the questions, we'll do some practice of that. So first question, I need to actually pull it up because I didn't have it. The first question was, how do 3D formulas for diagonals, point distance, and midpoint differ from the 2D formulas? Okay, well, that's what I was just talking about. The 2D formulas, we'll write them out, was simply a squared plus b squared equals c squared. Okay, now, and again, you have a, b, c there, but now we just think of it as length squared plus width squared plus height squared equals, and I could just say distance squared. The formula removes this and puts the square root there, but it's the same formula. So a squared plus b squared equals c squared, length, width, and height equals the diagonal squared. So it's really the same formula, but now with this added third element. Okay. Same thing with midpoint. Our original midpoint formula was just x1 plus x2. Find the average by dividing by 2. Then you did that with the y. Oops, we'll say y1 plus y2 divided by 2. And those were your coordinates. Okay, and now it's the same thing, but you have not only your x's, not only your y's, but you need the third dimension, so you just repeat it and do the same thing with your z's. You'll get a 3-point coordinate instead of just over here, x and y, you're going to get x, y, z. Again, forward, side, and then up. And again, we're going to practice that here in a second. So nothing new, just the third dimension. So number 2, it says to apply Euler's formula to this. This is a triangular polyhedron or a triangular prism. And so let's go ahead and try that, where we do again our formula. It's probably the trickiest part of this is just remembering it, that it's vertices minus edges plus faces will always equal 2. So let's go ahead and check that. Vertices are 1, 2, 3, 4, 5, and 6. Those are just all the corners. 6 minus, and then we have the number of edges, which are 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we've got 9 edges. And then we're going to add the number of faces, which are the 2 bases, 1, 2, and then the 3 sides, 1, 2, and then the one in the back, 3. So that means there's 1, 2, 3, 4, 5 faces. So if we check the math on that, -3 plus 5, it does in fact equal 2. So just practicing using Euler's formula, and you'll eventually get some problems where they're going to tell you the vertices and the edges, but you have to find the faces, or the faces and the vertices, you have to find the edges, something like that, just a missing variable. Since you know it always equals 2, you can solve for it. All right, number 6, these are just out of your textbook. We solved number 2 out of the textbook on page 674. And now we're going to find the diagonal, or actually in this case, a little more complex. They've given us the length and the width, but we don't know the height. But we do know this corner diagonal from there to there. So just think Pythagoras. We know that it's, I'll go ahead and write the formula out first. We can go length squared plus width squared plus height squared equals diagonal squared. Okay? And so what we know is we know the length is 6 squared plus 10 squared. Now we don't know the height squared, so don't put 13 there. That's our unknown variable. We know that the diagonal is 13 squared. So we get 36 plus 100 plus the unknown height squared equals 169. If we subtract 36 and 100, we get height squared equals 33. And so then we're going to find our height by just square rooting both of those. And so we get h equals either the square root of 33, if you want to leave it simplified, or that is approximately 5.7. So this diagonal here, or the height of this rectangular prism is 5.7. Okay, so just like Pythagoras, you just have the extra variable. Shouldn't be too difficult. But again, on this one, realize you're not solving for D. They actually given you D. They're giving you the diagonal. You have to go backwards and find the height. Oops, 7, 2. All right, and then a couple more. Number 8. Let's see. Number 8 is asking us to draw a cone in 3D space with radius 8 and height 4 units, with its base centered at 0, 0. Okay, so this is getting interesting. So here's the center of a circle, and it says the radius is 8. So that means it's going to come out 8. 1, 2, 3, 4, 5, 6, 7, 8. I can't really use my graph paper for this. I just kind of have to estimate it. To the right, 1, 2, 3, 4, 5, 6, 7, 8. To the left, 1, 2, 3, 4, 5, 6, 7, 8. And then in the back, 3, 4, 5, 6, 7, 8. Again, it gets 3D, so that's supposed to be more compressed. And so we've got a cone where this is our circular base. So that's the base. It's 8 spokes on distance, and then it's 5 tall. So 1, 2, 3, 4, 5. So then I've got the top of the cone right here. Just draw it like that. Okay, so there's my cone. It's 5 units tall, and then its radius is 8. It's a circle, so it's 8 on each side. And so now I have my 3D cone. Okay, so that's fun, but just learning to draw and represent things three-dimensionally on flat paper. And the last thing is, can we apply the distance formula and the midpoint formula to a series of points in three dimensions? Okay, so let's go ahead and first do distance, which is the same as diagonal. Okay, distance is just x squared plus y squared plus z squared equals d squared. All right, in this case, though, just remember x, y, and z are the distances between them. So the way I'm going to look at it is 0 and 7. If I subtract them, or I just think of the distance between them, that is 7. So I'm going to get 7 squared plus the distance between 3 and 0, which are my y's. That's 3, so that's 3 squared. And then 8 and 14. 8 minus 14 is 6, or the distance between 8 and 14 is 6, so that length is 6 squared. And that's going to be my diagonal squared. So let's go ahead and solve this. 49 plus 9 plus 36 equals d squared. If I add all of those up together, I'm going to get, let's see, grab it on my calculator, 49. We add those all up, I'm going to get 94. So 94 equals d squared. If I then go ahead and take my square root, I get d is approximately 9.7. So there's our distance formula, basically Pythagoras, but in 3 dimensions. And I could sketch all that, but there's no reason to even graph it, but you'd be able to see that the diagonal between them, I guess, there's no reason to graph it. It'd be roughly 9.7. So let's go ahead and then check out and do midpoint right over here. Okay, and if you remember, midpoint is the average of your points. Add your 2 x's together and divide by 2. Add your 2 y's together and divide by 2. And then add your 2 z's together and divide by 2. So same thing, we're going to pair them up. 0 plus 7, so that's just going to be 7 over 2, comma, then we're going to pair up our 3 and our 0. That's just going to be 3 over 2. And then we're going to pair up our 8 and our 14, and that's just going to be 22 over 2. Simplify those, you get 3.5, comma, 1.5, comma, 11. So the midpoint of those 3-dimensional points lies along the point of 3.5 forward, 1.5 to the side, and then 11 up. And again, we could graph that to confirm it, but I'm not going to waste your time doing that. We can talk about this in class. So here we go, 3D formulas, just like we've learned all the way back, going back to chapters 1 and 2, but now we've moved them into the 3rd dimension. All right, praise the Lord. We'll talk about this in class. Have a great day.